So, good morning. Welcome to Krishna's classroom. We now look at the so-called monotone convergence theorem, because we were discussing the convergence problems in the last lecture, and in the context we proved one theorem, namely the Fatos's lemma, which said the following. That is that if Fn is, let us recall it. See, we have a sequence of Fn is a sequence of non-negative measurable functions only, and we have Fn converging to F pointwise almost everywhere. Then our question was, what happens, what can you say about integral, the sequence integral Fn? And then we proved that then integral over E F, this is equal to, this is of course less than or equal to limit integral over E. So we are talking about the sequence, F. What happens to this limit of this? How is it related to F? And this is the sort of estimate that we have did. And we found that strict inequality may prevail in some examples. Therefore, obviously, the sort of questions that you ask at this stage is this: with what further conditions on the sequence you can assure that the equality will. Now, this is something very interesting to look at. What kind of conditions you have to impose on the sequence Fn. Now, we have looked at the example. The example was just conforming to this, and then we found that strict inequality would prevail. It is better to revisit that example, but I am not going to. Anyway, now what happens is, let us analyze this problem. So we are looking at this sequence. So sequence of numbers as it is. Now you see that you are talking about the integral of F. Okay, and what we prove is that you have anyway the limit of this may not exist. We don't know, it may not exist. Okay, but the limit will certainly exist. These are numbers with the limit will exist. So when is that going to converge actually? That's one question that you ask. So for that, you see, the lim may not be equal to the lim sup. So if lim is equal to lim sup, then of course the integral it would be equal to the two are the limit would exist. I mean, that is what we know about the number sequence. So we found that, or we know that if your sequence happens to be a monotonically increasing sequence, and of course bounded, then you see that the limit would exist. Otherwise, still the limit would exist, but the limit may be infinity. Okay, if it's monotonically increasing and convergent. Now you see that if Fn is a sequence which is monotonically increasing, then correspondingly this sequence also would be monotonically increasing. Therefore, you ask the question, suppose I put that condition, is it possible for me to get strict equality here? This is the question that we address in the what is called monotone convergence theorem. So let's take the statement of the theorem. Monotone convergence theorem. Let us take the statement of this theorem. Let sequence Fn be an increasing this is the condition that we are posing. Be an increasing sequence of non-negative measurable functions on E. So we are imposing the further condition that Fn is an increasing sequence of non-negative measurable functions on E. Okay. If the sequence Fn converges to F almost everywhere on E, then we get limit that means the interchange of limit and the integral is possible. Okay, it's quite easy to prove because you know that this condition, the sequence, barring this one, it satisfies all the conditions of the Fato's lemma. Therefore, we have this inequality Fato's lemma we have this inequality, namely integral over F Now, what we have is this. For every n, Fn is less than or equal to F almost. So, and is monotone. consequently what you get is this, that this is a monotone increasing sequence. Numbers. What more you get further? Integral over E Fn is less than or equal to integral over E Therefore, we can now work on this particular inequality. What does it say? It says, therefore, limit supremum of integral over E f is less than or equal to f. This is true. I mean Fn. So it comes from the previous inequality that we did. Okay? And that implies the following. Lim su Fn is less than or equal to this inequality is there. But in general, we have this inequality we already have. Okay? That's the general inequality that you have. And you have another inequality that lim sup of Fn is of integral of Fn is less than or equal to lim in for integral of F. So together implies lim sup of and that means the following, that is limit n tending to infinity integral over E and you see that integral of f over E is squeezed between this lim sup and lim in. So what does it mean? So by 1 you get the required relation, that is equality. This follows from the two inequalities. Now lim sup of Fn is this, just by 1 n. So that completes the proof. Okay. So you see that with one additional condition, namely it's a monotone sequence which converges to F almost everywhere. We get the equality. What is that? The Fato's lemma. And also you get this equality. That means interchange of the limiting process and the intersection. And the integration is valid. So now we can get a Q corollary from this. Let be a sequence of non-negative measurable functions on E if F is equal to sigma n equal to 1 to n, and pointwise that means this series converges pointwise almost everywhere to F on E, then integral over F that means again it's the same thing, it's a consequence of this, says that you can interchange the summation and the integration, which is not in general valid. So we'll give a proof of this, a Q proof of this. Choose then you see that Fn is non-negative and measurable functions on E, and this condition says that sigma n equal to 1 to infinity un converges to F almost, pointwise almost everywhere on E, means that Fn converges to F almost everywhere. So this means now Fn is monotone, increasing, and converges to F almost every. Converges to almost everywhere. Now, an application of applying the monotone convergence theorem converges to integral over F over E. But integral because it's a finite sum that you have, you can interchange the summation and integration. This is because it's a finite sum. Okay. This we have is equal to quality. So that's the consequence of this, in which form quite often we may be required to use it. Okay. Now it's a very important. So you see that in one of the examples that we have considered, where the equality does not prevail, you can see that this particular property of monotone convergence is violated. So that is in the light of this, one should try to look at the example, look at that particular example, and then convince yourself that it violates the conditions of the monotone theorem, so that you don't get equality, or in the Pato's lemma, apply to that. Okay, now we are in a position to define what are called integrable functions. Definition: a non-negative measurable function f on a measurable set E in fact that is redundant, it's called there is set to be integrable over E if integral finite. So that's the definition of integrability. Now we make some go back to the Chebyshev inequality applied to the integrable functions and what we can conclude out of that. So that's the next theorem. So what can you say about the integrable functions? Is there some property that is significant over there? In this context, I think we have made a mention of it earlier. Applying the Chebyshev inequality, we can come to certain conclusion. So let us anyway put it as a theorem. Let the non-negative then F is finite almost everywhere. Which means the set on which F takes infinite values is of measure 0. That means almost everywhere the function takes finite value. Okay, and that's quite easy to prove. It is just a one line application of Chebyshev's inequality. This is where you see how this inequality is applied. N be a natural number by Chebyshev inequality. And the monotonicity of measure we get what we do in Chebyshev inequality is to get an estimate for the set on which F takes large values. Okay, so this is what you do. Measure. This is what you have. Measure of x belonging to E, Fx infinity. This is a set of points where F takes the value infinity. So we are considering non-negative functions. And this is of course less than or equal to measure of where fx n for any n, this inequality is valid because of the monotonicity of the measure. Okay. Then by Chebyshev's inequality, this is less than or equal to 1 by n now you see that f is integrable. It implies integral over E, f is finite. Hence, it follows that this can be made arbitrarily small by taking n sufficiently large. Since this is valid for every n, you see that this has to be 0. That means f takes infinite value only on a set of measure 0. Okay. So this is the result. So that completes the proof. Okay. Now we ask another question, namely, suppose Fn is an increasing sequence of non-negative measurable functions. That is, of course, the condition that we have assumed in the monotone convergence theorem. Now, then we also, in the monotone convergence theorem, you recall the assumption that we made was it's an increasing sequence of non-negative measurable functions on E and Fn converges to F. Okay. Then we said that the integral of Fn converges to integral of F. Okay. Now in a way, we put the following question. Suppose we have the following, namely, Fn is an increasing sequence of non-negative measurable functions and integral of Fn is bounded. Then we want to say that f converges pointwise on E to a measurable function f that is finite almost everywhere on E and limit n tending to infinity integral over E Fn equal to integral over E f, which is finite. So that's the statement. This is called Beppo-Lewis theorem. Let Fn be an increasing sequence of non-negative measurable functions. On E. Now, in the monotone convergence theorem, we talked about Fn converges to, the sequence Fn converges to F almost everywhere, and then talked about the integral of Fn and integral of F. Here what we are going to say is the following. We are going to say something about the integral of F. So we are going to say that integral of Fn is bounded, that is assumption. Then integral of, then the sequence Fn converges pointwise on it to a measurable function f, and the integrals also integral f. That's it. If the sequence of is bounded, pointwise to a measurable function f, that is finite almost everywhere, and okay, so this is the difference. I mean, earlier we have made assumption about Fn converging to F almost every, pointwise almost every, and then made some statement about integral Fn converging to integral F. Now, what we are saying is this: suppose the sequence Fn is an increasing sequence of non-negative measurable functions, and the sequence of integral that you have, these are numbers, you see, that you construct out of Fn. So it is a sequence of numbers, and we assume that this is a bounded sequence. Okay. Now you see, from that you can come to conclusion about this, in the sense that it is a bounded sequence. Therefore, you can easily say that, and also this is a monotone sequence. Okay, it's a monotone sequence, and it is bounded, and therefore, what you can conclude is that the integral Fn converges to some number. Okay, therefore we can use that and to define the function f, etc. So that's how we proceed. Okay, right. So every monotone increasing sequence of extended real numbers converges to an extended real. What is an extended real number? An extended real number is R, the set of real numbers to which both plus infinity and minus infinity are adjoint. And then we have also said what is the sort of calculus that we impose on that with the objective or motivation of introducing what is called measure and integration theory that we have done earlier. So we are talking about R star, which is essentially R union plus infinity union minus infinity. Okay. So what do we have? What can we say about this? Suppose Fn is a sequence. We are not assuming Fn's are all bounded functions. Fn's are a sequence of is an extended real valued functions. Extended real valued therefore what you can say is that this is the following. These numbers to converge in R star. These are all non-negative. It's monotonically increasing. Therefore, it converges to a finite value or to plus infinity. And that's what we infer from it. So now we may define the extended real valued non-negative function f by f of x equal to limit n tending to infinity now this f may take even infinite value at some points. Okay, so f, because it's a limit in the extended real valued number system. So what you have is this, that is fx because it is extended real valued numbers that we are operating with. Now you can apply by monotone convergence here. What we get is this. Infinity. What more we have? We know that integral Fn is bounded. That's our assumption that we have made. Now what we know is that bounded, what we obtain is that integral over E F is fine. Therefore, by the previous result, F is finite almost everywhere on E. So that completes the proof of this theorem. Okay, so Beppe-Levis lemma also we have proved. So what the Beppe-Levis lemma says is that if Fn is a monotone sequence of functions with the property that integral Fn is a sequence of numbers which is bounded, then the sequence Fn converges pointwise almost everywhere to a function f which is integrable, and you also have this property integral fx is, this is also there further. And integral f is finite, and therefore you see that f is finite almost everywhere on E. So Fn converges to a function which is finite almost everywhere, and also the function is integral Fn converges to integral f. Now this is the Beppe-Levis. So now we have more or less completed our discussion on measurable non-negative functions. That is Lebesgue integral of measurable non-negative functions. So this stage is more or less complete now, and what we intend doing next is drop that non-negatives. Okay, and we talk about what are called measurable, Lebesgue integral of measurable functions. Now this we would consider in our next chapter, namely the lectures that are to follow. Okay, so our generalization has completed the third stage, and then now we are going to the fourth stage, which completes our task. Okay, so how did we start? We started with what are called simple functions, defined integral for that. Then next step was we looked at measurable functions, not necessarily non-negative, defined on E, and where the measure of E was assumed to be finite. Then in the third stage we got rid of that condition, but we introduced an ad hoc condition, namely that we were looking only at non-negative functions. And then the fourth stage, we consider what are called measurable functions, or the Lebesgue integral of measurable functions. So that's the next task. So thank you very much. Continue with this later.